Hello, everyone. This is John Dunnick. Thank you for joining our webinar on simulating bioheating and RF tissue ablation with COMSOL Multiphysics. Let me talk about what we're going to cover today. We're going to do a quick overview of COMSOL, very quick, and then I'll talk briefly, very briefly, about models versus apps. And I'll look at a range of different bioheating examples that are of interest to an audience such as this. Then what I'll do is get into the meat of the actual webinar, and that is I'm going to do a worked example of, in this case, a low-frequency tumor ablation problem. Now, as you folks in the industry know, RF tumor ablation can be, well, it spans a wide range of frequencies. For those of us that think in engineering terms, frequently we'll think, well, if you're talking about RF, you're talking about Maxwell's equations using wave analysis. We can do that. In fact, later in the webinar, I'll show you a couple of examples of that. But the industry also uses that for what I would think of as fairly low frequency things. So what we're going to do in these particular examples is we're going to look at a problem that we constructed out of the model library, and we'll start it actually at the DC equivalent. So we're running at a very low frequency, and then we'll do the RMS equivalent of a 10-minute run at a particular voltage, and then look at how that works. Then I'll switch it to an actual frequency analysis. So we'll change it from a DC equivalent to actually running things in, as an AC equation, and in this case at 1200 hertz, and talk about that. Now, those of you in the industry know that there are two things that you are, quite interested in as you're looking at these types of problems, and that is, one, what the temperature is that the tissue is going to reach. That is of obvious importance. But if anyone has actually had the misfortune of touching a hot stove, say, or whatever, as long as you don't put your hand on it and leave it on there too long, you're probably going to be okay. So the amount of time that you are exposed to the temperature is much more important. How much energy is absorbed? How much time have you been above a certain threshold temperature? All of this dictates whether or not you have some necrosis in your tissue or not. And what you're looking at on the right, where it's expanding, is the actual envelope of a tissue necrosis. In this case, it's 60% of the tissue or more or less is damaged within that envelope. And COMSOL makes it very easy to calculate that. So we're going to do that particular example problem with those three steps in it. But before I do that, this is intended to be, not live, but semi-live. And so there is a question-answer section. And if you type in questions, periodically what I'll do is I'll try to look at them and see what see what people are asking. I will assure you that we will be following this up with the attendees, that we have their contact information, and then sending the notes, including my step-by-steps of how I built this particular model. So there already was a question saying, gee, do I need to take a lot of notes? Well, no, you don't. And also I am doing a variant on a model library problem, so you should be in good shape that way also. So with that, let me turn and talk a little bit about COMSOL itself. I'm going to, since I'm running this this meeting, I've got a little panel that is blocking things. I'm going to close that up for a moment, and then I'll check it from time to time to see as questions are coming up. But one of the things that's really nice about COMSOL is it really is a multiphysics program. We are a single integrated environment, and by that what I mean is you can simulate everything from heat transfer, fluid flow, chemical, electromagnetics, acoustics, structural, all of this sort of stuff. And what's really nice about it is we treat all of those equations the same under the covers. Now, what does that gain you? Well, since we treat them the same, the user interface is the same for all of them. Well, the boundary conditions are different, what type of source terms you put in, but the mechanics are the same. And more importantly, you can mix and match anything with anything. And you're going to see a bit of that, because what we're going to be doing is doing various forms of electromagnetics that are coupled to heat transfer. And then actually under the covers, we're going to add what's called a damage integral. So it's actually yet another physics that gets put in there. And you can solve these things fully coupled or one physics at a time. In this particular case, we're going to do it one physics at a time just to go quick. Now, what's astonishing about this software is even though it is so powerful, it's actually really easy to use, and it's very easy to learn. We've worked really hard to accomplish that. What we have is a complete simulation environment, so you can build anything you want in COMSOL, from all the way up from the geometry on up, and you're going to have what's essentially a CAD-like interface. Now, we can also bring in things from CAD tools for geometry. Many people do that. But anyone who's familiar with the interface of a CAD tool is going to feel extremely at home with COMSOL. Everything you do is put into a model tree. If you want to change it, you just highlight those things, and we run the tree. So anyone is going to feel really comfortable. Now, for those people that want to build something that's even easier to see, what we have is this thing called Application Builder. Those people that are running on a Windows environment or a emulated Windows environment. So let's say you're on Linux or you're on a Mac. If you can get some of the emulation tools, VMware, there's a bunch of them out there. Then what you can do is run COMSOL in the Windows mode, and what we do is we give you tools to be able to change what we think of as pretty simple, but still even simpler user interface that can be run by people with just the salient things that you're interested in. Now, what's really nice about this is it's really two sides of the same coin. When you build an app, you still have a COMSOL model there. And so you can either run in the app or you can run as a COMSOL model. It's all the same stuff. It's just what is presented to the user. Now, what's really exciting is that you can build something in COMSOL, and then the user does not need to have COMSOL. What they have to have access to is another product we have. It's called COMSOL Server. And it's a global floating network license, and it's quite inexpensive. It's tenth the cost of a COMSOL floating network license, and yet it is a full global floating network license. So if you are trying to build something that non-COMSOL users are using, one, you can make it simple. Two, you can make it such that they can run it without having to purchase COMSOL themselves. Let me show you a really quick one that's not a heating problem. This is actually another bio problem that is a cell separator. In this particular case, it's using what's called dielectrophoretic forces. Let me just open that up. So I'm going to get out of this. Let's see if I can figure out how to get back out of this guy. Maybe escape. There we go. And then I'm going to open up this separator. And here's this COMSOL model of this. And bear with me. I know this isn't bioheating, but it's a nice example of bio. And then if you notice up in this upper corner is Application Builder. And if I pick it, I'm now in the builder mode, and someone has spent a bunch of time building a really beautiful model of this thing. This is exactly the same thing as this model. I mean, it's just two sides of the same coin. The beauty is that if I hit Test Application and we look at this particular model, what you're going to see is a much simplified version of that model. It's the same thing. It's the same engine under the covers. It's doing the same stuff. It's just that you, the user, have made it into a much simpler interface that you can then, send out to your fellow engineers or customers or whatever. And then if they have COMSOL or access to COMSOL Server, in other words, you can point them to that, they can run it. So with that, I'm going to close that out. That was my little ad for COMSOL Server. It's a really cool product. I'm going to get back out of that, and I'm going to go back down to heat transfer. So let's close up this particular app right here. We're going to be working in COMSOL. COMSOL is a product that is modular. We've got COMSOL Multiphysics, full-featured multiphysics code. But to it, you can add various modules that add more power to the tool. Now, the first part of the example problem that I'm going to run, by and large, will be done in base COMSOL. You'll see that I have this biological tissue in it eventually. That is going to depend on the heat transfer module, but that is the only piece to it. So actually the electrical part, when we're doing DC conductive, stationary, RMS, can be done in base COMSOL. But as I start adding, a frequency content to my electrical problem, then what we do is we run up into the AC-DC module. Now, if you really go full featured or full bore on RF, and it really is RF, so you're in the megahertz thing, you're microwaving or something like that, and there's plenty of things that may take that. Then what you are is adding the RF module. So everything that we're doing is based on COMSOL Multiphysics, but what we'd let you do is add different things to it to add capability to an already capable model. Now, this is the model that we are going to build, so I'm not going to dwell on this one. We're going to talk about this at a great length, but here is what's essentially Joule heating, electromagnetics. I will allude to this one. This is basically the same sort of thing. However, now what we have is honest-to-goodness microwave heating. So what we've got is a megahertz wave that is traveling down a catheter where the shielding has been cut down at the bottom. And so you see the waves escaping, acting like a simple antenna. Just like in Joule heating, JID, with some frequency terms and built into it, is going to turn into heat, and that heat, of course, will warm up the tissue. And then, just like what we did before, we're going to be looking at, well, where's the dead tissue and where's the not dead tissue. So this also applies for high frequency RF. That's not a redundancy right there. It's not the only way you can do it. We can do chemical heating. Here's a hip replacement. Those of you that have ever know someone or have a loved one that has a hip replacement or whatever, you know that there's two ways to put this in. You can either tap it in with a friction fit and wait for the bone to grow into it, or for those people that don't have bones that can support that sort of thing, they're older or whatever, then you use a cement to glue the hip replacement in. Well, the problem that you run into, of course, is that the curing of that PMA cement is a exothermic process, and bone is a wonderful insulator. So you could find that it gets too hot, and you actually could start having tissue necrosis in the bone, which of course would be a disaster. So we could do that. Other ways of getting heat, I'm sorry. If you've got a high intensity sound that is focused down onto some part of tissue, maybe a part of your heart or something else like that, the sound itself is going to lose energy just from viscous heating inside of the tissue, and that energy, of course, goes into heat. And so another way that people will use acoustic therapy, and COMSOL is extremely well poised to solve that. We've got a couple of examples of that. So that's just briefly a couple of examples that I have. Copy of the presentation, I commented about that. I will talk about the hypo versus cryo. I'm going to have an example of that. And then the question also says, for RF ablation, can you set up electric resistivity function? And absolutely, it's very it's very typically that it is a temperature-dependent resistivity. I will comment about that. There, what you have is two-way coupling between the two, the two physics, and I'm happy to show that. And then also there's this person has done this before, temperature dependent and irreversible for live tissue versus dead tissue. Hold on to that thought. I'm going to show you exactly where you set that up. From our point of view, that is a damage dependent material properties, and we have that covered. So just hold on to that. I can show you exactly where you do that. And let's see here. I'm going to get this question thing skidded over to the side here, and let's go back. So I'm going to walk through what I'm going to do with this worked example, and then I'm going to spend the last 20 minutes of the webinar doing the example. So let me cruise on through, and I'll show you what we're about to do, and then I'll build it from there. Okay, so I'm going to be doing the low-frequency Joule heating problem. This is one out of our model library if you have the heat transfer module. We've got a liver sample, live liver. So it's got an artery going through it. It's got capillaries in it. We'll talk about that. We have an insulated catheter, 4 probably nitinol tines that are acting as the electrodes. We'll do only half of it, so one, you can see it pretty easily, and then two, it's half the size, so it's quarter and solves 4 times faster. And then we'll talk about these infinite elements. Okay, now there's 2 physics involved right here, electric currents and heat transfer. You can enter that in one of 2 ways. We're going to do it one by one and then link them together. Or you could go into coupled heat transfer and say, gee, I'm going to do EM, electromagnetic heating under heat transfer, Joule heating. And then the beauty of that is we then add the physics and couple them for you. For the electromagnetics, we're going to ground the outer boundaries. We will have infinite elements so that they decay down. Again, I will talk about that. And we'll have voltages on the electrode surfaces. Now, I'm going to start by doing an RMS equivalent for this problem. Okay? So we're going to be looking at essentially a 32 degree or 31 volt AC circuit peak to peak. But if I wanted to do a DC analysis, it'd be the same thing as a RMS signal, or the DC equivalent of that would be 31 divided by the square root of 2, that happens to be 22. So let me go ahead with that. We've done, with the heat transfer, we're going to have very similar things. It goes down to T blood. There will be capillary perfusion in the liver. And we'll set the artery. We actually know the temperature of that. That's going to be blood temperature. So we actually could couple this to fluid dynamics. I've done that in problems similar to this and actually have flow going through there. But let's keep it simple for this particular one. Now, the linkage between these 2 physics is pretty exciting. We've got 2 linkages. This particular one that I'm going to do is the volt times amps is power. Power turns into heat. Well, that's J dot E. Now, if it's an AC analysis, it's half the real part of J dot E, which is the complex conjugate of E. Either one is fine. As you move up in frequency to true RF, then you'd have a very similar thing. And the idea is that the losses coming from electrical are piped into the source on the heat. Okay? What we'll do is we'll solve for electromagnetics and heat. Okay. Now, after this, we'll do both of these things for an RMS analysis of what's essentially DC. We'll move in and do a frequency analysis, and then what I'll do is I'll add the damage integral. And at that point, the person that was asking various questions about different material properties and things like that, it'll become abundantly clear what we do with that. And the goal, of course, right here is this particular plot right here, and that is the necrosis bounding and temperature distribution over time. In this case, it's 600 seconds. So let's go ahead and do this. So I'm going to get back out of here. Okay, I'm going to go into Model Wizard. And I'm going to choose 3D in this particular case. Obviously, we could do 2D. We could do axisymmetric, would be a similar thing. I'm going to choose, in this particular case, I'll start off with one physics. I'll do electric currents and add it. Okay, and you can choose any type of physics. You can add and mix and match a bunch of them at this point right now. But instead, what I'm going to do is I'm just going to add them one at a time and then solve it. So I'll go to my study. And I will choose to begin with a stationary analysis. So everything I'm doing up till now is basic COMSOL. There's no extra module involved. Later, I'm going to add a frequency domain one. Now, the minute I did that, I've moved into the AC-DC module that handles that type of problem. Okay? So I'm going to do a stationary analysis and then hit done. Do I want to save my previous one? No, I don't. So COMSOL launches its, wonderfully easy to use, user interface right here. I could go into the length unit. I'll change it to millimeters to make it a little bit more convenient. Now, I could just build this. There are a number of things I could do. I could right-click, and I could, use a import. I could bring it in from another CAD tool. I could go to one of the LiveLink products. But what I'm going to do is I'm going to go to the insert sequence and grab this sequence. I already built it in COMSOL once. Essentially, I went in and stole the geometry sequence from the previous model and then build that. And so here what we've done is we've built this entire model in COMSOL, and it involves a bunch of steps. And just to pretty things up, and I go into definitions and go to the view and not show the grid right here. And then I will close the geometry. Now, let me go on and start adding, parts to this model. What's nice about COMSOL is everything is listed in this model tree. So it's terribly easy to see what you've done. It's very easy to debug. So if I look at this, I don't have any materials defined yet, so let's fix that. I'm going to right-click. When in doubt, right-click, and I'm going to add a material. Okay? And if I could either add, I will choose it as a something from a material library, or two, I can do a blank material. So I'll do a blank material, and I will call these things the electrode. So the electrode. Okay, so the electrodes are right here. And I'm going to actually, you're going to laugh, I'm going to leave everything as an electrode because it's easier to amend things and edit rather than, pick this, pick that. So I'm going to put in the electrode conductivity. That is 1E8. You'll see what I mean in a minute. And then in this particular case, we don't have any permittivity, so we'll leave that as, well, what I mean is the permittivity is the same with free space, so epsilon r is 1. Now, obviously, it's not all electrodes, so let's go correct some of this stuff. So I'm going to right-click. I'm going to do add a material. I'm going to add the liver. Okay? So with the liver, what I'm going to do is go into what is part of our AC heat transfer module, and I'm going to add liver human and add that to the component. Okay? Now, when I do that, it says, wait a minute, I've got this entire thing made out of electrodes. What's made out of the liver? I'll pick this. And so I know a bunch of stuff about liver, but I don't know its conductivity and I don't know epsilon r. So let's go in and correct that. So I'm going to change the sigma to 0.33. Okay, and again, epsilon r in this particular case will make it 1. Okay. Now, the nice thing is these things are not part of the electrode. Okay, that's why I made electrode everywhere. It makes it easier. Things lower on the list take precedence over things higher. So let's do it again. Let's right-click, and I'll do another blank material. In this case, I'll call this one blood. Okay, so I'll do blood. And where's blood? Well, it's in the artery. It's also going to be in the capillaries. But let's go in. Blood's got a a higher conductivity. We'll make it a 0.66. Okay, and we'll make epsilon r be 1. Okay. So now I've got all of my materials defined. So let's go ahead and define where am I calculating the electrical properties. Meaning, where am I solving the electrical equations? Now, right now it says I'm solving everywhere. Now, I actually don't need to do that. I'm going to clear this out. I know what the the electrical properties are going to be, or the electrical results in the electrode. This is insulated, and this is where my voltage is. So I'm just going to calculate only in the artery and in the liver tissue. That was that easy. And so now it is not calculating anything in the actual cathode or electrode. Okay. So what is that going to be? Well, let's put that voltage in. So I'll right-click on electric currents. When in doubt, right-click. These are volumetric things. These are boundary things. So I'll choose a electric potential. And then what I want to do is to choose this electrode tip. Okay. So I'm going to go ahead and let's move my questions over. I will get back to questions in a minute. And then I'm going to choose the electrodes right here. Okay. And what I've got, actually grabbed the little tip right there. Let me take that out. Let me erase again, and I'll do it again. Just the electrodes right here. Okay, so now I've got the electrodes chosen. It depends on if this is metallic or not. We'll, in this case, say that it is not. And it wants to know what the voltage is. And as I recall, that was 31 volts. Okay, and we want to do the RMS, so we're going to do divided by SQRT of, let's see here. Oh, they're one-fingered typing here. Bear with me. Okay, square root of 2. Okay, so it's a 31 volt peak to peak, but we want to do the RMS version of it, so that's divided by the square root of 2. Okay, now let's ground it. So I'll right-click, and I will choose ground. Now what I want to do is to ground all of the top boundaries. So we're going to go down to ground on the top, and I'll pick all the bottom boundaries and go down to ground on the bottom. And then on this outer one right here and an outer here. Now, at this point, this is where the engineer in me starts getting really nervous, because we have a voltage here and we have a ground here, and I'm really nervous whether or not I've distorted the field. Has that gone down too quickly to ground? Because literally, I can drag this boundary in and sort of dial a solution. I squeeze that in, and all of a sudden the gradients go up. So in doing this problem like this, I have made a choice, and I want to change that. So what can I do? I can either make this a whole lot bigger problem, but that's going to cost me a lot in elements, so it's going to take longer to solve. Or two, I can use something that is called an infinite element. Now, let me set the geometry up to allow us to use infinite elements. These things are really cool. What I'm going to do is I'm going to put on a padding on the outside. So we're going to go into the layers, and this is in COMSOL on the cylinder that I just built, okay, for the tissue sample, and build that. So all I did is I just went in there and I added a 10 millimeter padding on the outside of everything. Now, that didn't do a darn thing to anything in the problem. All I've done is just made this particular problem have a couple of different zones in here. Okay. Now, what I then can do, if you do this, then what you want to do is to check, because you've changed your geometry. And no surprise, when you change your geometry, we try like mad to try to, keep up with that change, but obviously this didn't keep up with it. So the electrode's a little bit messed up. It looks like it has chosen something here in the liver. And I did this on purpose to show you that there's a potential problem that you can run into when you add this second. And if you're like me, you think of this after rather than, as you're doing it. You think, oh my gosh, wait a minute here, I need to correct that. So if you do what I just did, you want to go back and correct it. And actually, I'm dead serious. That's exactly what I'm doing. I almost always end up having to do this. And so again, with the electric currents, the same problem is occurring. I've got it's picked the wrong things. So I'll just clear it out again and then deselect the electrode. Oops, didn't get the deselection. Let's try that again. We'll pick the deselection box up right here. So this is, quite frankly, this is my standard routine. Oh, that may be my standard routine too. I forgot to select it. So we'll go in right here, and then I deselect the electrode. So the point was, make sure if you change your geometry, go back and check to make sure that COMSOL's kept up with those changes. So again, with the electrical, that looks good. We've got the ground on the outside. That looks good. Everything looks great. All right, so now we're in pretty good shape. We've got the ground. We've got the infinite element out here. I've corrected the things. Let's mesh it. So I'm going to go into my mesh. So we've got a lot going on. I'll collapse the settings right here, and I'll open up the model tree once again. I'll go to the mesh, and because I'm using infinite elements, I want to be a little bit cautious about how I do this mesh. I'm going to change it to wireframe. I'll right-click to the mesh, and then I'll add a free tetrahedral. And now what I'm going to do is not do remaining, but particular domains. And the particular ones that I want to do are the non-infinite element domains. So I'm going to go in here and carefully put a box around those. Okay? So let me build that, and I get a nice tetrahedral mesh for it. It looks pretty nice. These warnings are saying that some of the elements are tinier than specified, but that's exactly what I wanted. And then literally, then I'm going to do is I'm going to add a swept mesh and say how many elements to sweep the rest of it. It wants to do 5. I want to get a quick answer, so I'll make it 4. 5 is actually a pretty good number, and build all. And now we have the entire thing meshed. We are now in perfect shape to solve this problem. So let me go in, and we'll set up the actual solution, and then I'll go back to your questions. So let me right-click on right-click on Study, and hit Compute. And away it goes. It's now going to, wow. Well, let's get your questions in half a second. Let's go in and do an isosurface plot. Let's do, say, 15 of these things. Hey, how are we doing on time? We still got a bit of time. We're okay. All right. And plot that. And lo and behold, I get this beautiful, beautiful plot right here with the isosurfaces for the isopotential lines. Okay. Looks good. So let me look at some of your questions. I'm going to try to catch a couple of them. I won't be able to get them all. Okay, so, and we will get back to you individually on these things. Let's see, we did the hypothermic, and the AC module handle 100 to 200 million degrees centigrade. Wow, we're talking toasty. There's no reason that we can't handle it. I mean, what we're doing is we're solving the heat equation right here. The issue would be whether or not the, the heat equation as we're doing it, the classic heat equation handle is correct in that particular region. That looks like sun temperatures, I think, and of course the material properties are going to be pretty wild there. So in theory, the answer is we should be able to do it. Can we predict shrinkage and stress buildup and bonds? Of course, that would be a structural problem. We actually do have the ability to put, if you've got the structural mechanics module, you can add additional strains at all times that can change, and we do have things like water absorption and things like that. So the answer is yes, as long as you have the structural mechanics module. Let's see. Big pain. There's something about RF. This is a long note. I think I'm going to pass on this one just because I'm pressed for time right here. Let's see. Why are you using epsilon r of 1? Actually, just to make it simple. There's no reason that I didn't have to use epsilon r of 1. However, for this first part of the problem, we're doing straight DC conductive, and so it is not going to have the concept of E and D in it, so it's more for the rest of the thing. How does it know the infinite outer boundaries are infinite elements? Oh, that is a good question. Did I set up the infinite elements? Whoa, good job, whoever's out there. Let's see. I did not. Holy moly. Okay, so let's fix that. Right click. I'm going to do an infinite element domain. See how easy that was to check? And thank you, whoever that was. I really appreciate that. And I better get those things in there. So let's go correct that. So it's here, here, here. In fact, it'd probably be easier to just do this way. Let me shrink this question thing back down. Come on, right there. I'll shrink the question down there. And I'm going to erase them, and then the easiest way is align this properly, and then do a box select. I'll do the box select on the top. I'll do a box select on the bottom. This one and this one. Now I've got all the outer infinite element domains, and I'm going to do a cylindrical domain. Holy moly, I forgot it completely. So let's resolve this thing with the infinite elements. Right click on study 1 and hit compute, and now it will actually avoid that distortion problem that I was worried about. Thank you, whoever that was. And if you look at it, you can see the infinite elements properly, bending these things. It is essentially putting in exponentials for the shape functions right there. It's that's what I should have seen before. So thank you. So with that, given that I had to do a little bit of a correction, let me continue. Let's change this to an honest-to-goodness frequency analysis. Wait a minute. No, I've got to add some heat. So let's add a physics. So I'm going to right-click on a component, and I'll add a physics. Let me move this question-answer pane a little bit out of the way. And then I'm going to go in and I'm going to add heat transfer, and I'll add either heat transfer in solids or bioheat. In this case, I'll do heat transfer in solids and add that to the component. Okay, so now it says, okay, I'm going to calculate heat transfer everywhere. Excellent, that's what I want you to do. Now, I am going to have biological tissue in some of this, so I'm going to choose heat transfer in biological tissue. And it says, oh, you do? Where is this heat transfer? So I'm going to right-click, and I will do biological tissue, and I will choose this area, the middle part. What is a biological tissue to us? It's places that have capillarization. So the capillarization follows the Penny's equation, where we are simulating the capillaries as a distributed, heat sink or source. So it needs some material properties. So I'll go in and I'll add that. I'll do that through parameters. And I will read those parameters from a file. I already typed them in. So here they are. Okay, density, C sub P, the heat thermal conductivity, omega, which is the perfusion, the liters per second of capillary flow per liter of tissue, and then the blood temperature. So now let's go ahead and use those. So I'm going to go into Bioheat, and let's start typing these things in. So that one is T blood, okay, T underscore B, okay, and I've got to do the C sub P blood, so let me do that. C sub P underscore blood, okay, and the omega blood, OMEGA underscore blood, okay, and the density of the blood, that's rho blood, RHO, HRO, oh my God, blood. Okay. Now I could, if there was a metabolic thing going on, I could actually put a heat source in there if I wanted to. Now let's do a few more things in the heat transfer. I'm actually not worried about what the temperature in the artery is. So let me not calculate, whoops, I do want to do that, okay, in the artery. And instead what I'm going to do is just set a boundary condition there. So I'm going to right click, I will choose a temperature boundary, and I'm going to use the box select, and then box around those elements right there. Okay. Now, I think I might have caught the tip there. So let me deselect the tip just in case. Right there, yes, just in case. Okay. And then I'm also going to have right-click. I'm going to do a temperature boundary condition. Okay, and then that is going to be on all of the top boundaries. So I'm going to drive it down to T blood, okay, and then drive it down to T blood down at the bottom. Well, hold on here. I better orient it a little bit better. There we go. And we'll do the same thing down here. And then I'll just very carefully pick these outer boundaries right here. These are all going down to T blood as we're going out to the outer edge. Okay. We're now set. Okay. The only other thing I need to do, let me make sure that for once I didn't. Oh, that's right. I didn't set it at T blood. So let's change it to T blood. T underscore blood. This is again what makes this interface so nice. It's so easy to check these things. I'll go back down here. I'll go to T blood. T underscore blood. Okay. And that's good. I also want to start with an initial temperature of T blood. Now, some people say, well, wait a minute, the catheter was at room temperature, wasn't it blood temperature? Can you handle that? Sure. I could always do T underscore blood here. Okay. I could always go in and say right-click and put in yet another initial value and then set the catheter at whatever initial temperature I wanted to. In fact, I could actually do a separate analysis to see, it's been in the tissue this long, what temperature is this thing? So this is where COMSOL really shines. So now we've got a heat transfer all set up. Let me check my cheat sheet to make sure I've got everything that I was intending to. Oh, I've got to change the material properties. Come in here, the electrode is missing a thermal conductivity. So let me add that. Looks like K is 18. Rho is, what is rho? 6450. And C sub P is 840. Okay. Okay. And I believe we are all set. Now, I've got the temperatures set. For those people that are worried, wait a minute, you almost didn't do the infinite elements. If you notice, that's up at the component level. So it's already being used. So those of us that missed that the first time, I'm not going to have that problem the second time. Okay, so now let me go in and add a study. Right-click. I'm going to go in and add a study step. We'll do time-dependent. Okay, I'm missing one thing. I've got to link the physics in this thing. So let me do that separately. And I want to step by 10-second intervals, and I want to go for 600 seconds. Okay. And replace that. Okay. The thing that I forgot also is I've got two independent physics right here. What I want to do is I want to link them. So I'm going to do a electromagnetic heating. That is in the tissue right here. And then answering the question of someone that had asked, what about temperature dependent? Then what I do is I'd right click and I'd send temperature coupling to send the temperature back. And then I could solve them simultaneously. I'm not actually going to do that in this problem, just to make it go a little bit quicker. So in the stationary step, I want to solve for the electric currents. And then using that result, I want to solve for heat transfer. Let's go ahead and do that. Right click and hit compute. Okay. And away it goes. Okay. Now the next thing I'm going to do, and I'm running a little short on time, so I'm going to do this quickly, is to switch it to a frequency-dependent analysis. And then the third thing that I'm going to do is to fairly quickly add a actual necrosis calculation. Okay. So we're almost done here. Just waiting for that green bar to make it all the way across. And it looks like it's happy. Okay, so now let's go ahead and look at this electric potential. I want to add yet one more 3D plot group. I'm going to do this fairly quickly. I'll just leave it that name, right click. I will add a isosurface plot, and in this particular case I want to plot temperature. Okay. And we'll take the temperature and do it in degrees centigrade and plot that. And lo and behold, now we've got what this looks like as a function of time. Okay, so I could take this back in time, say 60 seconds, and of course it's smaller. Okay, now how would I change this to a frequency dependent? Trivial. Right click on study. And go to study steps. I'm literally just going to go to frequency domain, add it. Okay. I'll drag it up where the other one used to be. I'll get rid of the stationary one. Okay. And then I'm going to set it for 1 point, we're going to do it in kilohertz. And we'll do it for 1.2 kilohertz. Trivial. I mean, this is pretty easy. Now, remember, we had that RMS, so I want to change that. Let's see, we're not doing this in heat transfer. And we're doing the time dependent only for heat transfer. We're doing the frequency domain for electric currents. That's right. I'm going to go back up to my electrical. Now I can really use peak to peak. So let's get rid of this square root of 2 stuff. Yeah. And we're done. Now, this is a little bit different, so let's right-click, change the solver configurations. I'm going to delete these configurations so that it knows it. And then it's going to say, gee, do you want to get rid of the results nodes? No, I want them. And then literally right-click and hit compute again. We'll end up with exactly the same answer. Exactly. Mainly because we are not having any permittivity. Okay. Now, we are right at 11:45, so I'm not actually going to run this as my time on Pacific time. So I'm not actually going to run this. What I'm going to do is I'm going to come in and I'll just show you where you would add the tissue necrosis. It's pretty simple. I'm just waiting for this green bar to make it across, but I'll tell you what I'm about to do. I'm going to go into the biological tissue. And then there's going to be a section in there of calculate the damage integral. There are 2 types of that. There's either a temperature threshold one or an energy absorption one. The temperature threshold says, gee, if you're higher than a certain temperature, what's going to happen? So let's go look at that. Okay. If you are higher, I go down here in the biological tissue, include the damage integral. Okay, and you can choose one of energy absorption or not. Okay, let's switch it back from energy absorption to temperature threshold. And if you notice, we have 2 thresholds here. If you go above 100 degrees centigrade, you're boiling your temperature. So that obviously it's just not going to like that. But you also have typically like a 50 degrees centigrade for 50 seconds or more will kill the tissue. We have that both for high temperature and low temperature. So we can do a cryogenic one. Gee, if you freeze it, it's also going to do something bad. Or you can do energy absorption. The other thing that came up in the questions was, gee, what if there are different material properties? Literally, you just pick this thing and say, you know, if it's damaged, here are my material properties for the damaged tissue. If it's not damaged, use the original things. So now what we can do is turn on and off things like capillarization. You get the full features of anywhere you type a number, you can type an equation. So just for fun, I've set that up. I'll right-click and hit compute. So you can see that nothing else had to be done. All you do is just turn the thing on. With that, I'm about 2 minutes over, so I apologize for that. What you can do is go to our website and find out about this and other bioheating type problems. You can contact our office. We have short webinars of instructional webinars all the time. So contact the local sales office about that. You can come to our annual conference. We have COMSOL days. There's all types of ways to learn more about that. But with that, I think I'm going to sign off, and I want to thank you all for attending. Thanks a lot. Bye-bye.